This presentation discusses the impact of time-step frequency on the realism of robotic manipulation simulation for objects of different scales. High-fidelity robotic manipulation simulators are necessary to create digital twins for smart manufacturing. This presentation uses the pre-assembly part picking task shown in this video to demonstrate context simulation for robotic manipulation. Reconciling physical behaviors in simulation with behaviors in the real world, called sim-to-real, is important to increase adoption of robotic systems for manufacturing. However, the physics of contact in hardware disagrees with physics in simulation, and this is called the sim-to-real gap. In this work, we evaluate the impact of the simulation time-step frequency, measured in simulation steps per second, on the simulation accuracy. Next, we evaluate the impact of the scale or size of the manipulated part on simulation accuracy. The experiments are described in the abstract, and we release our simulation videos and data publicly. We pick an inserted part and a base part. We find that a simulation time-step frequency, which accurately models contact, depends on the physical properties of the manipulated part. Small-scale objects generally require a higher time-step frequency for accurate manipulation simulation. Experiments show the impact of time-step frequency on simulation accuracy. As we see in this video and corresponding trajectory error plot, a smaller time-step frequency reduces the simulation accuracy, resulting in the part slipping within the grasp or being dropped. Increasing the time-step frequency improves the simulation accuracy. There is a well-known trade-off between the simulation accuracy and speed. Increasing the time-step frequency increases the simulation runtime. These results are a reminder of this trade-off, which becomes more pronounced when simulating the manipulation of small-scale objects. Experiments show the impact of part scale on simulation accuracy. As we see in this video and corresponding trajectory error plot, a smaller part scale reduces the simulation accuracy, resulting in the part slipping within the grasp. We also wondered whether the relationship between time-step frequency, scale, and simulation accuracy holds when the robot and object are closer in relative size. An additional study, which halved the robot size and kept the grasped object at the original scale, shows the simulation still requires a high time-step frequency for accuracy, suggesting small-scale manipulation generally requires finer temporal resolution. In conclusion, objects of small scale require a higher time-step frequency for simulation accuracy. Adaptive time-stepping could balance the stability-performance trade-off, possibly through adaptively substepping the simulation or simulating different objects with different time-step frequencies. This work was made possible by the Foxconn Interconnect Technologies, the U.S. Department of Education, and NASA. We would also like to thank the members of the UIUC FIT Cobot Factory project for their support. Thank you very much for your attention, and we look forward to further discussions in the poster session.